All right, so I was just working through this second video, and my camera sort of cut out on me and I lost the video. So I have a lot of stuff written here that I'm going to go over, but just know that I had already worked through it, so I'm kind of just talking through the work that I already did. So in this example here, we're going to be taking two angles, A and B. A is an angle that's known to be in the first quadrant. B is in the fourth. And we are also given more information. We're told that sine of A is 1/2, cosine of B is 3/5. And what we're asked to do is find the tangent of A minus B. Very first thing that pops into my mind when I see this, tangent of A minus B, is that I want to use my difference identity, which we just derived for the tangent function. So that is given here, tangent of A minus tangent of B, 1 plus tangent of A times tangent of B. But I don't know tangent of A or tangent of B. I need to see if there's some way of finding those values. Well, one thing that would help is recognizing that tangent of A is equal to sine of A over cosine of A. That's from our identity for the tangent from back in chapter 7. Tangent of B is equal to sine of B over cosine of B. So that puts things in terms of sines and cosines, which I have a little bit of information about. Now, before I jump to that, take a look at this first thing right here. Sine of A is equal to 1/2. To me, that looks familiar from the unit circle. I know, for example, that sine of pi over 6 is equal to 1/2. I also know that sine of 5 pi over 6 is equal to 1/2. So I know some angles that would give me this. But if I want to narrow it down to a single angle for A, I also have to use the fact that A is in the first quadrant. So which angle lives in the first quadrant and has a sine of 1/2? Well, that would be pi over 6. We know that for sure. The inverse sine of 1/2 gives me this. That's another way of coming up with that. I can't quite do the same thing for B because 3/5 is not something that I recognize as a value that comes out of the unit circle that I have memorized. So I need some other way of working with angle B. So coming down here, here's where I did that work. Tangent of A is equal to sine of A over cosine of A. But we just determined that A is equal to pi over 6. So I can plug pi over 6 in directly. What is sine of pi over 6 and cosine of pi over 6? That's 1/2 and root 3 over 2. Dividing those and simplifying gives me root 3 over 3. Alternatively, if you remember your unit circle for the tangent function, we already know that tangent of pi over 6 is equal to root 3 over 3. So I could have jumped straight to that answer as well. What about B, though? Tangent of B is equal to sine of B over cosine of B. And we actually are given cosine of B up here. We know that it's 3/5. So that's one thing that I could plug in. You'll notice here I wrote negative 4/5. How did I get that for sine of B? Well, I did that work over here. Because we're working with sine and cosine of the same angle, I know that the sine of B and cosine of B are related to each other by the Pythagorean identity. Cosine squared of B plus sine squared of B should equal 1. If I already know cosine of B, which is 3/5, I can plug that in. 3/5 squared is 9/25. If I subtract that from 1, getting the common denominator and everything, that would give me 16/25. So working this equation out, solving for sine squared gives me this. Sine squared of B equals 16/25. Okay? I am looking for sine of B because over here I need sine of B to be able to put that into my numerator. I can find sine of B by taking a square root of both sides. But it's really important to remember that when you take square roots of both sides of an equation, you're supposed to be putting a plus or minus here. And our goal is to narrow this down to either the positive answer or the negative answer. One of those is correct and the other one is not. So how do I do that? Well, I go back and use the other information that I'm given about angle B. B is an angle in the fourth quadrant. And because we're taking sine of B here, and sine only gives us negative answers in the fourth quadrant, this has to be negative 4/5. It cannot be positive 4/5. So that's where this negative 4/5 is coming from here. Dividing and doing the division, I get negative 4/3. So what happens from there? We come back up here to where we had our difference identity worked out. And now that I have values for tangent of A and tangent of B here and here, I'm substituting these in for tangent of A and tangent of B here. You can see that happening right here. The rest of the work is arithmetic, so I'm not going to talk through all that. It's simplifying complex rational expressions, working with radicals, all that stuff, which takes a little bit of time, but You've done a lot of that up until that point. So my final answer is given here, 3 root 3 plus 12 over 9 minus 4 root 3. Okay? Now this is where I had ended my last video unexpectedly when my camera cut out on me. So I'm going to pick up where I left off here. And I'm going to change what I'm doing in this last step, because after having a second to look at it again, I realized that that approach was not going to help us. There's a different approach that we want to take. Let's look at what we're doing, though. We're proving in an identity. Cosine of x plus y times cosine of x minus y equals cosine squared of x minus sine squared of y. Now, when you're doing a trig identity involving a plus or a minus for one of the angles, like we are here, that's generally going to be the side that you want to start with. In 9.1, we said that a good general strategy is to start with the most complicated side of an identity and simplify it down to the simpler side. And when we're working with sum or differences like this, we're generally always going to assume that that's the more complicated side. The benefit of starting on the left-hand side here is I can go straight to my sum and difference identities. Okay, so cosine of x plus y times cosine of x minus y. Cosine of x plus y is the same thing as this. This is my sum identity for cosine. Cosine of x minus y looks like this. That's my difference identity. Now, comparing the things in these square brackets, they look almost identical. The only difference is that I have a minus in one of them where I have a plus in the other. And if you think about this in terms of how you do factoring in algebra, this is a product of the form a minus b times a plus b. That, from algebra, we know gives us a difference of squares, a squared minus b squared. Or in this case, cosine of x cosine of y squared minus sine of x sine of y squared. Okay, and then if I actually square those, it's the same thing as cosine squared of x times cosine squared of y. We have that property of exponents that lets us distribute exponents over products, minus sine squared of x sine squared of y. The next step that we're going to do is very non-intuitive. So I don't really expect people to think of this next step. That's what makes this identity hard. So you just kind of have to see me do it. And then I'm going to say that this type of thing that we're about to do is fairly common in calculus. It's a fairly common technique in Calculus 1 and Calculus 2. And what it has to do with, what we're doing is we're actually going to make this more complicated before we can make it simpler. There's various different ways of doing that, but basically what I'm going to do is add something to this and then subtract that same thing, because that's essentially the same thing as adding 0, which doesn't change a quantity. So I have cosine squared of x, cosine squared of y here, and I'm going to add a new term that wasn't previously there. I'm going to add cosine squared of x sine squared of y. And it's not going to be immediately obvious why I'm doing that. But we'll see where I'm going with this in a second. Now this minus sine squared of x sine squared of y is being carried over from the previous step, so that was already there. And then notice I can't just add this new term in here, because then I have something that's not necessarily equal to this. I've introduced a new term. So if I want that term to be there, I have to compensate by subtracting it again over here. And combined, this term minus itself is equal to 0. So by introducing these new things here, I've basically just added 0 to the previous expression, which is no different than what I had before. And at this point, you're obviously asking, why would you do that? That's way more complicated looking. The reason for that is because now I can group up these first two terms and these second two terms and factor something out. Notice that both of these have a cosine squared of x in common. So that gives me cosine squared of x. And what's left? Cosine squared of y plus sine squared of y. I'm going to do something similar here. I can factor a negative sine squared of y, because that's showing up in both terms. I'm bringing the negative out with it. Negative sine squared of y. And what's left in parentheses here? Well, because the negative came out, I have a positive sine squared of x. and plus, because again the minus came out, that's a plus now, cosine squared of x. Sorry, 1 second.